You're watching Grassroots TV.
Good evening. I'm Ginny Galisa now with Rocky Mountain Institute, and thank you so much for joining us tonight for RMI's Quest for Solutions. Our topic for this RMIQ is Factor 10 Engineering. We have a very impressive group of panelists who Marty Pickett will introduce you to later on this evening, and all of them, every single one of them, flew in from some of the other part of the country to join us tonight. So one little bit of housekeeping. We are being recorded by Grassroots TV, which means that if you have a question during our Q&A period, you'll notice that there are microphones on all of your tables. There's a little button that you push to the side and speak directly into the mic when it's time for you to ask a question. And, and our moderator will remind you of that later on as we move forward. So, it's been an interesting economic time, hasn't it? And because of that, we are so fortunate to have an amazing group of sponsors, both corporations and individuals, who stepped forward this year and said, you know, the RMIQ lecture series is so important that we cannot not support this. And so if you will indulge me, I would like to take a moment to really honor these individuals and organizations who are supporting us right now today. The first one is RMI's National Solutions Council. We have a number of members here in the audience, and what makes our council very different from other national councils is that our members commit to a number of different things. They commit first to being ambassadors for RMI in whatever part of the country or world they are in. Secondly, they choose a project that they are going to sponsor every single year. And this year, they chose to sponsor the Smart Garage project or our acceleration of electric vehicles. And NSC members, would you all do me a favor, and if you're comfortable, would you please stand? Okay, nobody's standing. And just to let you all know, we actually do have members of the MOVE team here tonight, and anything you want to know about the acceleration of electric vehicles, go look for them because they would love to talk to you about it. One of them is right back here, Matt Matella, and Christine Chan Lizardo is right over here. So the next part of this is, I'd like to recognize some of the firms that have supported us. Cottle Carr Yaw Architects is one of the longest supporters of the RMIQ lecture series. Ryan Investments, Chris Ryan. Let me tell you, over here at RMI, we are so thrilled that he's doing a great job managing our investments. Michael Fuller Architects, another original sponsor of the RMIQ lecture series. Steeplechase Construction, who I know is doing a great project, a green great project down in El Jebel Basalt, I believe. Aspen Sojourner. Nancy Mayer, Michael Miracle, great articles in here on sustainability. You all have one at your tabletop. And Victoria's Espresso and Wine Bar, I don't know where they are, but I hear that Victoria's is a new, latest hot spot on the mall, and they have the best coffee in the valley, and they are hosting our wine and cheese reception later this evening. And I want to take one more moment to honor some of the, there we go, some of our unsung heroes. And those are the RMI staff who worked really hard to make all of this happen. And Liz Bauer, phenomenal job, Liz. Carrie Sullivan, Davis Lindsay, Alok Pradham, Francis Woolley, and Shelley DeBeck. October 1 through 3, RMI is going to San Francisco, and we are reinventing fire. We hope that you will join us at this fabulous annual symposium. It's the first time we're taking it out of our home state. For those of you who attended RMI 25, imagine that in San Francisco. We have another great lineup of panelists. Peter Darby, who is the CEO of PG&E, Bill Joyce, the co-founder of Sun Microsystems, Tony Malcolm, Empire State Building, Ray Anderson of Interface, Carl Bass, who's the CEO of Autodesk, and many, many others. We'll be looking at the pros and cons of nuclear energy, corporate sustainability, you name it. We hope you'll be there. Come. So now, the main part of the evening. A man who needs absolutely no introduction, our co-founder, our visionary, our chairman, our lead scientist. All of us here admire and respect him, and many of us love him, Amory Lovins.
Thank you, Jenny. Thank you all. I'd like to suggest that many of the world's problems are caused by bad design, and we can fix it at a profit. As my colleagues and I run around the world redesigning lots of things over the years, probably over 1,000 buildings, various vehicles, lately $30 billion worth of factories in 29 sectors, we notice something rather odd. We see the same design mistakes repeated all over the world. For example, practically all houses around here have furnaces. Well, we found in Old Snowmass down at the Banana Belt, it's actually cheaper up front not to have a furnace, but to put your money instead into super insulation and super windows and ventilation heat recovery. So that made the house $1,100 cheaper to build in 1983. And by reinvesting that money plus some more, totaling $1.50 a square foot, we were also able to save half the water, 99% of the water heating energy, about 90% of the household electricity. The whole thing paid back in 10 months. That's 1983 technology. If you come for one of the 2 o'clock Friday tours, you'll find what 2009 technology looks like, because Judy and I just renovated the whole thing. It was starting to look sort of like a technology museum, but now it's up to date and will work, I think, even better. But why is it that practically all houses have furnaces that it would be cheaper in capital cost, not just in operating cost, not to put in the first place? Well, because if you read the engineering textbooks, and we've checked all those in English, they say that you should compare the extra cost of adding more insulation with the present value of the fuel that it will save on your heating bill over the years. That sounds perfectly logical. You don't want to put in more than it's worth, do you? But it's methodologically wrong, because that comparison of just operating costs saved by adding more insulation leaves out the capital cost of the heating equipment.
Could we get you to turn that mic up just a hair?
I can't, but somebody in the back can.
Thank you.
Okay, thank you. Yeah, systems without feedback are stupid by definition. Now, if the textbooks teach how to optimize the insulation wrong, then of course all the engineers will do it wrong, because that's what they're taught. Or take another example, and I want to spin this out at a little more length. How many engineers are in the house? Good. I think the rest of you will get this example too. One of our panelists, Mike Bertolucci, worked many years for and still advises a wonderful company called Interface, maybe the greenest company on the planet, led by our trustee, Ray Anderson. And they were building a carpet factory in Shanghai, since relocated to England, but they needed to move some heat around for heat transfer from where it was made to where it would be used. And a top consulting firm said, yeah, here's how you design the pumping loop, and it'll take 95 horsepower to run the pumps. So we brought some ideas from our wizard, Mr. Lee in Singapore, to a Dutch engineer, Jan Schillem, who was designing the thing, and he redesigned it to use about 7 horsepower, roughly 92% less, and yet it cost less to build, and it worked better in every respect. And this was not because they used a different process or controls or motor and pump design, but because they made 2 changes in the design mentality. The first one was to use big pipes and small pumps instead of small pipes and big pumps. Now, the friction in a pipe goes down as nearly the 5th power of its diameter. For example, in putting some pipes in our house, we just went from 1/2 to 3/4 inch pipes, and the friction went down by a factor roughly 7.2. That doesn't take very much fatter pipe to get rid of most of the friction that the pump is fighting against. Now, guess how the engineering textbooks tell you to pick the right diameter for your pipe to get the right amount of friction? They say, compare the extra cost of a fatter pipe with the present value of the saved pumping energy over the years. This is the same mistake. It leaves out the capital cost of the pump. What else? No, it counts the pipe, the pump, the motor to run the pump, the inverters and electricals to feed electricity into the motor. All that stuff is sized to overcome the friction, right? So it has to be big enough, and if you reduce the friction, you can make the equipment smaller. So actually, when you optimize just the pipe by itself as a component, just for one benefit, save pumping energy, you pessimize the system. If you optimize the whole thing together, from the pipe all the way back toward the power station, and you optimize it for saving energy and capital cost, 2 benefits, not one, you end up with teensy little pipes and motors and electricals, and the whole thing costs less to build. So that sounds kind of a good idea. Why isn't it in the textbooks, we wondered. The other change in design mentality was even simpler, therefore more difficult. That's to lay out the pipes first, then the equipment. Normally we do it the other way. We put the tanks and boilers and so on in some arbitrary or convenient or traditional place, and then you call in the pipe fitters and say, please come connect point A to point B. But by then, A and B are pretty far apart, and there's other stuff that got in between them, and they're at the wrong height, and they face in the wrong direction. So by the time the pipe makes its way all the way across the space, all dressed in neat right angles like they teach us in trade school, it has about 3 to 6 times the friction it should have had with a straight shot. Now, the pipe fitters think this is great. You pay them by the hour. They mark up a profit on the extra pipes and fittings. They're not paying for your bigger pumping equipment up front. They're not paying for your bigger electric bill forever after. But for you as owner, it would be a lot smarter to have fat, short, straight pipes rather than skinny, long, crooked pipes, right? This is not rocket science. This is good Victorian engineering rediscovered. We used to know how to do this stuff before the different design professionals in the value chain got all siloed and stovepiped and stopped talking to each other. Or if you're designing a car, suppose you made it lighter so it didn't take as much force to make it go, and then you could get the same acceleration out of a smaller engine. Well, the first time an automaker looking at regular production models did a serious examination of how much of the lightweighting could you pay for by making the powertrain smaller was maybe 2 years ago. That's a pretty basic level of design integration, and it's like how much insulation can you pay for by making your heating system smaller? And more than enough to get rid of the heating system is the answer around here. We've done the same trick getting rid of air conditioning up to 115F in ordinary-looking tract houses with better comfort and lower construction cost. Well, this principle of optimizing a whole system for multiple benefits rather than isolated components for single benefits turns out to be extremely powerful. I laid out how to do it in buildings, industry, and transport in some lectures at Stanford Engineering School 2 years ago, which, by the way, just came out in Chinese. We hope they'll be used to train the whole next generation of Chinese energy experts. That would be revolutionary. And as we see how needed this rethinking of design is and all the design principles that go with it, we see that we've really stumbled on a revolution even more important than the stunning advances in technology for wringing more work out of our energy and other resources. To be sure, the technologies continue to advance very, very quickly. They keep getting better faster than we use them. So efficiency is an ever bigger and cheaper resource. But even more important, and until now overlooked, is the integrative design art of how do you combine the technologies into integrated packages that make big savings, very big savings, cheaper than small or no savings. In other words, instead of being stuck with diminishing returns to investment and efficiency, the more you save, the more and more steeply the cost goes up until it gets too expensive and you have to stop. We're finding a new realm of expanding returns. Like at first I get diminishing returns adding more insulation to our banana farm, but then I get to the point where it's so well insulated, twice as well as normal, that I no longer need the furnace, ducts, fans, pipes, pumps, wires, controls, fuel supply arrangements, and it ends up with a 99% heat saving, cheaper up front than if I tried to save little or nothing. And why should I get there the long way around when I can tunnel through the cost barrier to that design destination? So this is the revolution we're hatching in an ambitious project, one of two main ones we're driving in my office of chief scientist, led by Lionel Bonny and Alok Pradhan, and it's called 10xe, Factor 10 Engineering, because in many cases we're finding you can indeed increase energy and resource efficiency by a factor 10, sometimes more. There's some examples more like 100 or 1,000, but I'll settle for 10 or close to it. But with lower capital cost, violating everything you might dimly remember from business school that says more efficient stuff costs more. Yeah, it does if you buy a little efficiency. If you buy a whole lot of efficiency with integrative design, it can cost less up front. And we've demonstrated this now in so many buildings and vehicle designs and factories that we think it's pretty generalizable. One of the more fun examples recently for EDS will be completed next month in England. It's a data center that's expected to use a quarter the usual amount of electricity to produce 4 times the desired amount of computing. That's a factor 16, except it costs about 10 or 15% less than normal to build. Had they felt able to follow all our recommendations, they would have saved about 95% of the electricity and half the capital cost, and still would have gotten 4 times the expected computing out of it, so that would be about a factor 80. Our latest chip fab design for an unnamed client is expected to save 2/3 of the energy and half the capital cost and eliminate all 22,000 tons of chillers. Our latest mine design for a very large mining company doesn't use any fossil fuel or any grid electricity. It runs on gravity, which is very reliable. Of course, you wouldn't get to those results with what's in the engineering textbooks. So what we're talking about is nothing less than the nonviolent overthrow of bad engineering by fundamental reform to how engineering is taught and how it is practiced. So we're trying to figure out some good ways to drive integrative design into both pedagogy and practice, that is, retreading in-service design professionals across the full range of design disciplines and applications. People are hardwired for storytelling. So we think the best way to teach this stuff, and it's how we actually do it when we're working with clients on real designs, is through case studies, through examples. So the centerpiece of 10xe, toward which we now have working groups cooking up the case studies, will be a casebook that we want to write about a year from now in a summer study. That means you take 2 or 3 dozen gifted people and lock them up for a week or two, and they write a book. Except this casebook will be a little unusual. It's not a text, although a text may later emerge to go with it. It will instead give the traditional disintegrated design solution on one page and the integrative design solution on the facing page. So by the time you've read to the bottom of them side by side, following the flow of the design logic and the calcs and drawings, you'll understand how the second way uses 1/10 the energy or other resources of the first way, and yet it costs less to build. Not because you came up with some screwy new engineering concept, you're just rigorously applying orthodox classical engineering principles, but you're asking different questions, so you're getting different answers. You know, just like when Don Runkle co-led the development in 1991 of the GM ultralight car, they took out most of the weight and drag, so it took a teensy little engine to run it, and got better packaging and better everything else. Just think where GM would be if that had become a model for production cars. Well, we're both still working on that one. Now, of course, we can't just write a textbook and spread it out to the enthusiasts here and there around the world who want to use it. And we've enlisted, 80-odd practitioners and deans of engineering at leading institutions who really want to change how they teach the stuff, and practitioners who want their practices to gain breakthrough competitive advantage. We want to create some demand pull to drag this into the market, just like Walmart and its suppliers have demanded, or Walmart has demanded of its suppliers, double efficiency trucks, and has enough demand pull to drag those into the market, so it'll double its own fleet efficiency by 2015, but then everybody else can buy those trucks too. So then we can amplify that into a 6% saving on U.S. oil, and then triple efficiency beckons after that. So how do you make demand pull for a change in design? One way we've thought about is when the casebook is through its beta testing among our sponsors and colleagues in industry and ready to roll out, we'd like the deans of engineering at the leading schools around the world to start getting calls from the CEOs of the companies that traditionally hire most of their graduates saying, sorry, we can't hire your graduates anymore unless you teach them in this new way, because otherwise they won't be able to produce the breakthrough results that our competitive success requires. And the deans we ask say, well, gee, I've never had a call like that, but it would really get my attention. I'll bet I'd start changing how we teach this stuff faster than the usual time constant of change, which is one funeral at a time. I actually was lecturing on advanced design integration for radical energy efficiency. I do this at various engineering schools around the world at ETH Zurich a couple of years ago, and I noticed the students getting rather restive. And as soon as the question started, they turned on their professor sitting amongst them and said, why aren't you teaching us this stuff? And one of the professors thought fast and said, oh, well, actually just last week my colleagues authorized me to set up a student faculty commission or committee to examine changes in how we teach. Who wants to play? Every hand went up. Now I need to go back and see what happened. I got almost that good a reaction recently at Cambridge, which is probably the finest engineering school in Britain. This is starting to get pretty encouraging. Another method of demand pull would be to have an article we've been invited to do in a leading business journal, which would cause business leaders to say, hey, there's this great new source of competitive advantage out there. It's kind of like Six Sigma or safety culture. It's called, what is this, integrative design. Get me some of that. We think that'll have some effect. We're drawing in interesting partners. McKinsey, for example, will be collaborating in ways we're working out now to make this as good as it can be, and they have some interesting channels for getting it into widespread use. Autodesk is one of our sponsors and collaborators, and they too have wonderful channels for changing how people design things. In their case, they do a lot of the important design software and know many of the designers. We're working with the Design Futures Council, which is the CEOs of the top 20 design firms in the world, who all want to transform their practice for competitive advantage and the benefit of the design industries and those that it serves. These are, I think, promising developments, and we're starting to get some really good cases coming in, but we are still on the prowl for wizard-class practitioners, outstanding cases, other kinds of support. We need people, money, ideas. I think we now have a venue for the event. And over the winter, we will be hatching some very interesting plots. This is one of the most consequential things we've ever undertaken, I think, at least as much as figuring out how to get profitably off oil, or the work we're doing now in reinventing fire to combine the profitable path off oil with one off coal. In other words, from oil and coal to efficiency and renewables. We're making very good progress with that. So far, it's looking a little easier than we thought. But I want to emphasize how simple these ideas about design are. That's what makes them difficult to grasp at first. But I think we have enough examples from buildings industry and vehicle design now that it's enough to teach and learn from everybody we need to be in this conversation with. And we found a funny thing. If I want to change how somebody designs a chip fab or a refinery, I'll show them a building like our house. If I want to change how architects and engineers design buildings, I'll probably show them a chip fab or a refinery. Because if we use examples from somebody else's discipline, then it's non-threatening. And they can absorb the design lesson without thinking, who is this guy trying to teach me my business? So we have much more fruitful conversations with a great diversity of examples. And that's why I hope some of you in the design arts or just in what you run across in your varied and interesting lives will help us find the best examples and people to make the first edition and subsequent editions of the 10xe casebook into a revolutionary tool, because this is not about the world of design, it's about the design of the world. I hope that that important task is enough to start off a stimulating conversation, which we'll have now with a remarkable panel we're very honored to have here, and I'd like to invite my colleague Marty Pickett, our Executive Director at RMI, to introduce the panel. Thank you.
Thank you, Amory. And I will say one new award that Amory is going to be picking up in New York in October is Cooper Hewitt's Design Mind. And so I think you now understand why he was the leading candidate for that award. As our panelists come down, I'd also like to say again, welcome to all of you. It's great to see so many familiar faces in the audience and also some new ones. And for those of you who are new to RMI's work, please know that we are a nonprofit. That explanation of our mission is on your program, but we work across 4 sectors: transportation, buildings, electrical systems, and industrial processes. And I would like, before I introduce the panel, to introduce, or not introduce individually all of you, but a few of our key employees at RMI, and then I would like to just recognize all of them so that you can identify them to talk with them later. But our CEO, Michael Potts, who's from our Boulder office, is here with us tonight. Stand up, Michael. And thanks, Michael. And we're also really lucky to have both of our program directors with us tonight from Boulder, Stephen Doig, and also Robert or Hutch Hutchinson with us. And if just the rest of RMI staff from both Boulder and Snowmass would stand so that you can see who they are, and you'll see that most of us have RMI name tags on. Please stand. RMI folks. We will be having a reception afterwards, so I really encourage you to seek those folks out to talk about what you'll be hearing tonight, but also other work that RMI is doing across those 4 sectors. So again, welcome to our panel. I think I'll start with the folks who have had the longest friendship and colleagueship with RMI for many years, Dr. Bertolucci and Nancy Clanton, I would say probably equally period of time. Nancy, who is sitting to my far right, is the president and founder of Clanton Associates in Boulder. She happens to be one of the world's best lighting specialists, along with Sardo, who's in the audience somewhere. So Nancy will be bringing her perspective of energy efficient buildings, many of which she's worked on, many of which she's worked on with RMI, actually. It mentions, I think, in her bio, the greening of the White House some years ago, but most recently with the Empire State Building. So thank you for being here, Nancy. Dr. Mike Bertolucci hails from Atlanta Interface Corporation, where he is recently retired, but no longer stopped working, certainly, as the vice president of the company and president of the Interface Research Corporation. He's been instrumental in the success of Interface as being a real leading corporation in climbing Mount Sustainability, as they call it, and has certainly set an example for the rest of corporate America. So thank you for being here, Mike, who will bring his firsthand knowledge and perspective to the panel. Thank you, Mike. Amory mentioned RMI's new partnership with Autodesk, a large software company that has software for education, government, architectural services, engineering, you name it. And we're really lucky to have with us tonight John Kennedy, who is a mechanical engineer and also a senior manager there, who will bring another perspective, particularly from his work with buildings and the barriers that we have with those in the real world. And obviously, one of the things that we're really interested in partnering with Autodesk is how can we, through this collaboration, figure out a way to put RMI's approach and 10XZ into the actual software itself. So thank you so much for being here, John. And our moderator tonight is Arjun Gupta, who is on RMI's Board of Trustees. He also serves on the Aspen Institute Board, has a home here in Aspen when he's not in San Francisco, where he leads his company, Telesoft. But more importantly, he has real background in energy efficiency, which you will see come out tonight as he brings leadership to this conversation. He has been the chairman of Nexent, a premier provider of consulting services and software in the global energy industry. For the last 8 years, he has overseen his company Telesoft's investment and served on the board of Amberware, a spinoff from MIT. It's a materials company with core technology innovations that provide insights into efficient solid-state lighting materials. And more recently, he personally and his company are a founding member of Cleantech Group, and he particularly of Cleantech India. So welcome, if you will, Arjun Gupta and the rest of our panelists.
Okay, thank you. So I think how we'll do this, I'm delighted to be here and welcome all the panelists and welcome all of you. We'll go through a whole set of sections. As you can tell, the topic is fairly complex, but Amory did bring it up to a summary level, which is very absorbable by all of us. We'll start with just a few kind of 3-minute stints from each of the panelists on their experiences. We'll then go into a whole bunch of different areas. Some of the things we thought about was, why do we need 10XE, trends in economics, barriers, where do we go from here, how do we get it done, and finally, next steps. And we'll open it up. I'll take a few pointed questions given the backgrounds of the various panelists, and we'll open it up to Q&A right after that. So first, as Marty mentioned, Mike has been a real titan about climbing Mount Sustainability. He has a PhD from Caltech. He has numerous patents both on the in material sciences and other areas. So Mike, why don't you take us through the fundamentals of sustainability?
Well, I guess we're probably going to have about a week here. I have a spare minute. You know, the old problem is it's not what you don't know. The problem is what you do know that ain't so. And that clearly came to me very clearly when I first went to work for Ray Anderson about 13 years ago, in which Ray had just read a book by Paul Hawken, The Ecology of Commerce. He says he had an epiphany. I think he had more of a vision about what the future could look like for an industrial intensive company, manufacturing company, that wanted to do things differently, and not just to be different, but also to be competitive and to be a winner, and to basically fundamentally take nothing from the earth that's not renewable and do no harm. Well, that's a very interesting and easy little catchphrase to say, but when you're the R&D manager and responsible for making that happen, things get a little bit more complicated very quickly. 13 years ago, there wasn't a big RMI pushing things like Factor 10 engineering, for example, which are very important and critical tools for people that would have a challenge, like making an industrial company off the grid, for example, and not using any renewable fossil fuels, and not loading toxic waste into the landfills, and minimizing their use of any kinds of energy to an absolute minimum, and then offset the difference. That's basically what this Mount Sustainability looks like. Those are the challenges that were laid out to us. Not only did we have the challenge of getting it done, but we had the challenge of describing it to other people who were interested in going up that mountain along with us, in a way in which they could understand it, and in a way in which they could mimic some of the rules, and from which we could learn, which is a critical part of trying to become more sustainable and to work with partners like RMI, for example. But it goes even deeper than that. When Marty talked about a long-time relationship with Amory. Amory was one of the principal members of what we called our dream team, because we just really didn't have a better name for it, and they didn't like it, but we called them that anyway. And they helped us with the fundamentals about how we get started, and they were very, very stern critics of things that we thought were important to do, that made a lot of good sense with regard to Wall Street, because we were a publicly traded company, but weren't really going to get us on a meaningful path to what a sustainable corporation could really look like. So I owe Emory a lot for any little success that I might have had of helping Interface get to where they are right now, which is about 50% of the way up that mountain, and we have a goal of getting there by 2010. And I'll stop now because I could talk forever on this.
The numbers on greenhouse gas emissions are?
Yeah, we're like about 95% really down if you include the RECs and the offsets that we produce. This company now only emits 68,000 metric tons, and we produce a few 100 million pounds of carbon.
Thanks, Mike. Nancy, you've obviously been a extraordinary and early leader and expert in things like daylighting, energy-efficient design, and reducing light pollution. Most recently, you were invited as the leader for the lighting group for the C40 Summit. How do we get this done? How do you really make it pervasive? How do you make it successful? How do you implement it easily? What are your experiences with sustainable design?
Well, it's interesting, Amory, that you brought up design of the world. You know, I thought that was so cool, because in my background, being an architectural engineer, and I'm one of the few more engineers here, we forever have had a linear design path. It's kind of like taking a rope and trying to pull people. That's really tough for us engineers. You know, we want factor of safety, we want to make sure that we're covered liability-wise. So to bring engineers along, I really think is one of the hardest way to do it. So instead of this linear approach of an owner going to an architect, then, as we engineers say, fix the architect's building, and then going and to a contractor is looking, go, what the heck? How did they design this? They obviously know nothing about building, but so the contractor fixes it, and then you're handed back to the owner, the whole thing. I keep envisioning, like the globe, the world, kind of a circular design path, where if designers and engineers need to start with their better education, And the professors really need to be educated in this new design process. I keep thinking at Rocky Mountain Institute, what a place to be, to get the ones that have done it well, bring the educators here, because some of these professors are terrified of anything new. Get the visionaries to come and work in a safe environment, teaching them how to do it. Then we've got the workforce out there that understands about the whole building concept instead of just your specific discipline and fixing the building. No, it's working with the architect and working with the landscape architect and that whole design. Then coming back and then getting education, feedback from the builder, what's going on. But most importantly, it's the people that occupy the building and the owner. I've always imagined, I drive a hybrid, and you know that constant feedback on my miles per gallon? What if we had hybrid meters or smart grids or something on every single home, every single desk, on your icon, on your laptop, that you could go, okay, how am I doing right now? Then go back, and guess what? Go back to the visionaries, go back to the educators, and we have a circular feedback loop. So I know a lot of us are frustrated. It's like, oh, global warming, carbon footprint. How do I begin? I think feedback from everyone is going to be such an important way of doing this whole thing. So I'll stop there.
Thanks, Nancy. Actually, it's coming. There's a product, I just saw a business plan for a company called TrackSmart that'll actually give you your energy utilization right on your iPhone or your BlackBerry.
Awesome.
So you know it 7 by 24.
Perfect.
But moving right along to John. John is with Autodesk now, as Marty said, but prior to that, he was president and CTO of Green Building Studio, which was acquired by Autodesk. And John's been in this whole field since 1997 when he presented his resource sustainability thesis to the Clinton administration's material and energy flow work group. John, given all the complexity of this problem and this whole kind of crisis, both financially as well as energy-wise, is this really a opportunity in some ways to take advantage to really move mankind kind of 10x and even 100x beyond where we are right now?
Yes. Yeah, it is. It's an enormous opportunity. And I think we are at a point in history where essentially we've been presented with a perfect storm of all these crises going on the planet, and all these people looking for solutions, all these people looking for creative ways to save energy, creative ways to replace the energy systems that we have in place. At the same time, enormous amount of funding is being made available to move us in that direction and create jobs. And also the synergy is the technology that's available. We are, if you look back in the early oil crisis period, a lot of technology didn't exist back then that would be able to save an enormous amount of energy. And that's really completely different today. We have multiple solutions in terms of technology to choose from the full price spectrum. Everything from, as an example of a building, a typical building, you can go with a plain restroom, or you could go with marble and gold. And generally you aren't justifying the price difference there from an energy saving standpoint. But today we have solutions of a similar variety across the energy efficiency scape. And I think that, coupled with everyone looking for solutions, not only to create jobs but to save energy, is a massive opportunity that is presented to us. So I think it's a really exciting time for us to be, alive, working on this solution, and our kids are definitely going to benefit from this. So I see it as a very positive thing that we're going through.
Terrific, thank you. I think you mentioned the perfect storm, and we might just be there. What I'll try and do in the next few minutes is kind of go through a little bit of the vision, some of the economics and capital required, or questions, and the panelists will give us some sense of it. Changes to the education system, just creating a broader ecosystem of educators, academics, standards bodies, licensees, practitioners, and finally move towards the next steps as it moves. So Amory, how did 10xe actually start? What was the catalyst? What is the right threshold? Do we really need a 10x improvement? What if we only get 4x? You gave the example of one of the clients that didn't take quite all your recommendations, but did take some.
Yeah,
What is the
I got
decision-making
only
process?
16 instead of 80,
Go ahead, please.
but still cheaper. Yeah, whether you're concerned about jobs and prosperity or national security or climate and environment, we ought to do the same things about energy, and the main thing we need to do is wring a lot more work out of it so that we can get off of fossil fuel and into the synergistic combination of efficiency and renewables. That's sort of obvious, and it solves a lot of problems at once: oil, climate, proliferation, a lot of development problems, a lot of global instability. I just did a paper for the Pentagon last week they seemed to like about all of the national security benefits that could flow from a really concerted focus that indeed the Pentagon is about to help lead on energy efficiency in what they do. But this is, again, not an abstraction. There was just a slightly muddled but basically helpful article in the Wall Street Journal, half-page article last Friday on our banana farm. And the reporter spent about 8 hours looking at our renovation technologies down in Old Snowmass. It took about an hour to interview our plumber. He's been a master plumber for 30 years, and it turned out nobody had ever asked him before to do low-friction pipe layout, like running pipes diagonally instead of with neat right-angle bends. Why neat right-angle bends? Well, they're customary. They look pretty, but they don't save energy and money. And in fact, the reason we did it originally was to make it easy to draw, but now we have wonderful software to draw our pipe layouts. The computer will do the work. You don't have to make it easy to draw. In fact, the main thing I taught this plumber, he knows a lot more about plumbing than I do, is just to lay out the supply pipes as if they were drains, right? Because there's another part of his brain that knows if you put a right angle bend in a drain, it'll clog. So you have sweet bends, or you run diagonally and design the bend out altogether. So what's the result? Well, we have a 0 to 45 watt pump to circulate hot water the length of our building. Normally, it would take 7 pumps, and it would total upwards of 1,000 watts. So you can imagine that was a pretty good investment. But nobody had ever asked him to do it before. Another thing about pumps, if I could take just a second on this, if you feed 100 units of fuel, let's say coal, into the Craig power plant, you lose at least a third of the two-thirds of the energy at the plant. You lose some more in the grid, and then there's all these compounding losses through the motor and the mechanical drive shaft and the pump and the valves and the pipes and so on. And 1/10 of the original fuel energy comes out the pipe as flow. Now turn those compounding losses around backwards into compounding savings, and every unit of flow or friction we save at the pipe, like laying out the pipes as if they were drains. Every unit of friction we save there saves 10 units of coal and cost and global weirding back at the power plant. Huge leverage for climate protection. So why do I dwell on pumps? Because they're the biggest use of motors. The second biggest is fans, which have the same physics. Together, fans and pumps use half the motor energy in the world. Motors use 3/5 of the electricity in the world. Making electricity accounts for 41% of U.S. fossil carbon releases. This stuff adds up. It's a lot of pipe bends. You know, it's the cracks around my window. It's a lot of little stuff. It's not just looking for some silver magic bullet in technology. We need to change the design mentality all the way to the practitioners, the plumbers, the electricians, the builders who construct this stuff the way they've always been taught to through infectious repetitis. You do it the way you did the last one. Well, design isn't about repeating the old design, it's about making it better.
Thank you. Nancy, on your projects in sustainability, what is the criteria for success? How do you really measure a threshold level of success which is enough, so to speak, as opposed to what you could academically get to?
Wow. Success to me are people that love the building. They are proud of their buildings, they want to be in them, or area. I mean, I'm not going to just say building, because maybe the area is outside, and your neighbors like it. So it fits in, it feels good, it smells good, it's just daylight and views, and hopefully the engineering systems are minimal. They're not noticed. I love a building when no one even notices that the lighting itself, because they walk in buildings and they notice surfaces are being lighted, and we have task lighting, and everything is personalized. I can control my whole system, whether it's mechanical control or personal control. It is this personalization that is the success of the building. Now, the great news is you do that, and all of a sudden, oh my goodness, you are using minimal energy use. The more layers you can give someone and the more personal control and the better the views, that is huge success in sustainability.
Thank you. John, Autodesk clearly has millions of customers worldwide. How do you jumpstart this whole ecosystem? And are there champions or industries, Amory happened to mention Walmart in his opening comments, that are more ready than others, that will be kind of thought leaders or be influencers to create a more broad-based system?
There's definitely low-lying fruit that everyone is focused on, and I think the primary one are buildings. And buildings, not many people realize, are the largest contributor to greenhouse gas emissions.
They're 70% of U.S. electricity.
Right, which is, for the large part, coal-based. And so that's how come you get this large portion in the market contributing from buildings being the largest greenhouse segment, is the example Amory gave of this coal unit of energy at the power plant being used at the electricity and the 10 times factor going all the way to the coal plant. And as I mentioned earlier, the technology exists today to actually make buildings efficient, cost effectively, and save money. Amory has numerous examples of that that are mentioned. And the thing, there's certain barriers, though, to that industry. There's the engineers that have been mentioned where they have the normal approach of things. There's the realistic factors in the market, for instance, in the commercial sector. A large portion of them have what are called split incentives, where you have your owner and your tenant, and each are somewhat motivated about something, but neither one is really charged with footing the bill to save that benefit. And these are real barriers that are going to be accelerated to be dealt with and solved in the very short term. In terms of this low-lying fruit, governments around the world really recognize this. And you're seeing some of the most aggressive regulations being put in place. And to give you an example how serious these governments are with regard to the relationship to climate change, is the Bush administration signed into law in 2007 when one of the most aggressive energy requirements for buildings, and that's the Energy Independent Security Acts, which goes into effect this January, requiring all new federal buildings and major renovated federal buildings to be designed to reduce their fossil fuel use by 55%, which is pretty significant. And what you find today in design firms is they aren't really sitting with the enormity of that challenge in terms of designing that. And escalating that to the millions and millions of buildings around the world, it's an enormous task. And so we really feel fortunate enough in our position at Autodesk to really have millions of users who are using tools that we feel that we can accelerate that transition.
Thank you. You brought up the role of government. I'm just going to open it up to all the panelists. What is the role of government? Is it doing enough? Can it do more? Are some parts of the world more with it than others?
Well, I'll take a little piece of that, and that is clearly one of the roles of government is to provide incentives. When you talk about the trillions of dollars that are being proposed to be, to go out there and to stimulate the economy, to create jobs, et cetera. Well, that's all well and good, but where's the direction on what kind of jobs are we talking about? And what are going to be the criteria for success in using that money, other than just increasing the GDP? because I can think of a lot of things that would do that very effectively, and at the same time put us at carbon, that put us at CO2 concentrations in the atmosphere that plants would be growing so fast, it wouldn't be any room for us. So.
Nancy?
The role of government. Well, one thing out there that I would love to have changed, and we're trying to in California right now, we talk about energy codes and regulations, and many of you in the design community work with them. You figure out your power density, for lighting power density, which is watts per square foot, and then you have mandatory controls. And as soon as the building is built and you get your stamp certificate of occupancy, it's done. Well, that's not energy. That's power density code. One thing we could do is to change it to energy and get feedback constantly to expand the role of energy commissions or the states to look and get feedback on energy bills. And if someone is really high, then notify them with, I suppose penalties, whatever. But then say we can come in and help you figure out why. Are your controls not working? Is it something else? Has someone changed equipment, taken all of Amory's straight pipes and put bends in them? I don't know. But what is the issue with it? And again, it's at full circle and getting people to look at it. But I think that the role of regulations to change power density to energy would be huge.
I think government should steer, not row, but there are some pretty nice trim tabs for steering in the right direction. You mentioned the executive order. Well, in the military, the Army Corps of Engineers, which one might not normally think of as a hotbed of innovation, has a working group now designing zero net energy or net positive buildings, that is, buildings that will create more energy than they use, and we'll be helping with that. We've actually designed some buildings like that already for others with good economics. You could in federal practice for procuring design services, pay the designers for what they save, not for what they spend. We've done 5 experiments at RMI proving that works. I think if that were what the General Services Administration and the Pentagon did in paying architects and engineers, it would help change private design practice pretty quickly. And the good design firms love it because it distinguishes them in a crowded market, and they get a fair reward for their extra talent and effort. The bad designers won't like it because they'll be worried about paying a penalty for underperforming, and they'll have to improve if they want to stay in business. You could do fee-bates. We've talked about that in other RMIQs for cars. You go buy a new car and you pay a fee or get a rebate, which and how big depends on how efficient it is compared with others of that size. Well, you can do the same for buildings. It's a sliding scale hookup fee. You pay the utility or the utility pays you depending on how efficient your building is. Unlike building codes, which are a good start but are obsolete before the ink is dry and give you no incentive to do better, a fee-bate would drive continuous improvement. That's, I think, something important when the technology and the design arts are both evolving so quickly. We don't want to get stuck with old practices and kind of cast them in concrete, literally.
Actually, your answers, both Nancy and Amory, just struck me that is this a time where you fundamentally have to overhaul almost how we measure and what kind of codes and standards that we have for the entire system first? And second is when you were talking about the dirty power, which John brought up, as well as the amount that's going in, do we have to re-regulate or rethink how utilities are regulated?
Well, yeah, in fact, half the states are now including, well, I think maybe soon including Colorado, are considering a regulatory reform that would, some have adopted it already, that would reward the utility for cutting your bill rather than, as is now the common practice, for selling you more energy. That's just dumb. We ought to stop doing that. That will have a very pronounced effect on utility culture and behavior when their interests and the customer's interests are aligned, and That's the biggest barrier busting we need to do for electricity and gas. But I think also, and this is not perhaps so much the role of government, we need to support great engineers. We got two of them right here, another over here. There's several I see in the audience, in their personal journey of rethinking how they design stuff. I mean, you didn't start off this way, right? you had to figure it out.
I did.
And what was that like?
Well, I have to tell a little story about Amory. He came and reviewed one of my projects way back in the 80s, and he says, Nancy, this is not efficient lighting because it's not direct. It's not coming straight down. You've got light hitting the surface and everything. And I said, well, Amory, what's your metric? He said, well, foot candles. I said, what about equivalent sphere illumination? He perked up. He said, tell me more about that. And ever since, it's like changing how you think. Getting your metrics to be quality and not just numbers, I think is huge. And what Amory is talking about, incentivizing utilities for energy conservation, it's decoupling of profit. In California, they do it. The California utilities are spending a lot of money on conservation because they no longer can make profit by selling energy. We need that completely throughout the country. And I hope Colorado's coming. This is good news.
But Nancy, you've invented a lot of the modern art of beautiful, efficient lighting with a handful of people. There's some others here too. And you've had to recruit engineers that were thinking out of the box and realized there's no box. You have built up a practice of this. You've started to influence the profession profoundly. Didn't you get the President's Medal of the Illuminating Engineering Society for this? You go, bro. But
so I think it.
But what is this like? Being the trailblazer. And having to make up as you go how to do great lighting engineering in a profession that, didn't do that much before, and most of the lighting is designed by electricians, electrical contractors, and interior decorators. It's neither beautiful nor efficient.
Basically, it is thinking about the end result and getting feedback and knowing there is a relationship between our healthy being and views and daylight. I mean, what I would love to do is not have electric lighting at all in buildings. During the day, every building should be designed. So maybe I'm working myself out of profession as electric lighting designer because it would be great to do other things, but it's really, there's night, but different things.
Yes, bringing it to individual initiative is critical. And to that point, Mike, you obviously went through this whole process of designing a new plant in China. Take us through almost like a mini case study. How did your management team think about it? What were the issues that came up? Were the economics just so compelling that you had to do it? Was it more a sustainability goal? How did you manage the economic versus non-economic factors?
There's a mouthful. Let me kind of start at the beginning. It's nice when you have a growing operation and you want to put a new facility in a new country to serve an emerging market. That's the first thing. Secondly, and I think one of the things that's probably unique, or at least at the time was unique to Interface, and that was what is the driving force and what characterizes Interface in everything that it does. Not only just building plants and building processes, but what kind of plants, where are the plants, what kind of processes, what kind of raw materials are you going to use, and what is the product that you're going to make, and then what are you going to do with it after you make it and after its end of life. It's a holistic approach about everything associated with it before you do anything, including figuring out how much it costs. So when we decided to build a plant in China, which no sooner had we got it built, we found out it was a bad idea, and we had to decommission the plant, which is a problem. It's a fact of life. It's something you have to deal with. But in the process of building this piece of equipment, in order to build it, consistently with the vision that the company had with regard to what a sustainable company could look like, you had to at least minimize everything that you were doing. Not fire people, but create an operation that used the absolute minimum of energy, therefore emitting the absolute minimum amount of greenhouse gases when the darn thing was on, and to produce products that use the absolute minimum amount of raw materials, which ultimately are non-renewable, or else renewable over a very long period of time, and to do it with the quality and the performance expectations that the customer has for the product, and to do it at a price point that your customer can afford. All those things mitigate what it is that you do and how you go about it. But you have to be concerned about all those things in order to make a breakthrough like our engineer Jan Skillum did when he designed that manufacturing plant to put a backing on a piece of carpet tile made from bitumen and a bunch of other interesting chemicals. And to do that in a foreign atmosphere, no pun intended, but not to get famous, but just to do his job within the context of what the job was at Interface. And as it turned out, because we have friends like Amory and RMI, where there's some learning that can go on, understanding friction and understanding the power of 5, et cetera, to design a plant that ended up with small motors and big pipes. So I'm not sure it answers all of your questions, but there's an underlying element here as well that helps influence the way engineers can think. How you allow your engineering staff to think is part of this process of how innovation can in fact occur. If you do things the way you've always done them, you're going to get what you always got. And I'm certainly not the one who said that first, but it just keeps coming back into my mind that you have to create an environment in which people are allowed to fail. Not crazy, stupid stuff that's going to bankrupt your company, but a freedom of intellectual freedom that allows them to wake up in the morning and say, oh my God, I can't wait to get to work to try this little deal because it's going to be fantastic. Oh, and the fact that it's going to make my company famous and I might even get a raise, that's a kind of a thing that's nice to happen. It certainly was the situation I found myself in coming to work for Ray. Ray had just let go the senior vice president who was running the research corporation because he just could not get out of his box and follow the vision that said we need to understand and define what a sustainable company could be like, and you guys have to figure it out. Make some mistakes, but I expect you're going to be successful. He couldn't get there from here. Here, what am I? I'm a Caltech PhD writing textbooks for graduate school, R&D managers for General Electric Chemicals and Plastics for 15 years, working for Union Carbide before they did Bhopal. I learned how to do things all the wrong way, and I worked really hard and got very good at it. I kept Jack Welch out of jail for a long time. So to get into that environment that I'm trying to explain to you, that I wish you all get an opportunity to get into sometime in your life, no matter what it is that you're doing. But when you have a sense of freedom to allow your brain to just go where it needs to go and wake up in the morning with that aha moment, that's what it's all about. That's what things like Factor 10 are all about. Tools that are available to you, that are brand new, that are out there, that are shiny, people don't know quite how to use them. Grab them, get them, work with them, see what happens. You'll be successful.
Thank you. That was very insightful, and I think you did answer my question. It was extraordinary leadership that went forward, had the vision, found a great partner with RMI, implemented it, and they actually did get the savings they were looking for. So John, clearly again, going back to Autodesk, in this kind of infancy of the industry, there's a lot of innovation going all over the world and individual practitioners. So Autodesk clearly is a proprietary software developer and producer and vendor. What is the role of open source, viral movements? Is there some version of a Wikipedia-like platform that can bring all these ideas together that evolves to the real set of tools that the world may need?
Definitely for sharing ideas. There's forums that engineers use today who are in this sort of challenge of trying to find solutions, and there's a lot of brainstorm going on in this sort of ecosystem of the internet that we have in a variety of ways, from the newer medias of Facebooks and LinkedIn and things of that nature to just standard old bulletin boards and news feeds. But I see where, in terms of open source and the tools that people use, I don't know if that's exactly a solution for the practitioner who's designing, the professional engineer who's moving forward on this new domain. One of the reasons for that is, this stuff is fairly complicated, and it takes, engineers with know-how, years of experience of failure and success to understand what to do right. And some of these systems that we analyze are extremely complex. And what we see is the investments needed to be put into tools and the training, the technical support. I really don't see open source as being able to provide that bigger picture to be able to rapidly move us to the realm where we need to be, where every design is sort of sustainable.
But we're planning to open source the casebook, and wouldn't that drive a lot of proprietary innovation? Because then your competitor can do it too, and you better do it first.
Yeah, I think so. The knowledge sharing is critical to be open, and there's no issues with that. And that happens today, in a forum like this, throughout the world, textbooks, people get ideas, formulate new ones. But in terms of, taking these complex issues, the case studies really illustrate a different way of thinking. But there's still a sophisticated analysis that needs to occur to actually fulfill the design, design it to be able to be constructed, to be manufactured. And some of these things are fairly complex. I mean, just if you look at a building to be designed to be net zero, you're going to have to understand the local weather conditions every hour of the year. You're going to have to understand all the material science in the building associated with how heat is transmitted, all the lighting technology, all the moisture movement throughout that building. And this is science that, really needs to be embodied, maintained, and continued in a really structured manner is the way Autodesk feels from a software standpoint. We can provide that support, that continuous evolution of that sort of software.
The underlying principles, though, are arrestingly simple. That's what's hard about it. You only get to simplicity through complexity, and right now our design arts are in the complex phase. I think Einstein said that he wouldn't give a nickel for the simplicity on this side of complexity, but he'd give his life for the simplicity on the other side of complexity. That's what we're all trying to get to. So, take the Empire State Building as an example. That retrofit's expected to save 38% of the energy with a 3-year payback, and that's several times the savings they thought they could get cost effectively. But the principle for doing that is, again, quite simple. We take out the 6,500 windows, not all at once, and remanufacture them on site in an improvised window factory that Serious Materials will cook up. Nobody's done this before, so you don't have to move stuff around the city and throw away glass. You remanufacture them into super windows that block the loss of winter heat by at least 2/3 and block at least half the unwanted summer heat gain. You stick the windows back in, those plus lighting retrofits and a few other things, then have to cut the total cooling load on the hottest hour of the year by 1/3. So now instead of having to close and dig up Fifth Avenue to renovate and expand the old chillers down under there, you can renovate them in place and reduce them and save so much capital that it helps pay for everything else, and that's how you got the great economics. Now, of course, the details of how to do that take a very high level of design skill and great tools, but the principle of doing it, optimizing the building as a system, not the components by themselves, that's the simple part. that we need to get across, and that we would love all the training and tools to teach those great designers how to do, so it becomes second nature. And that's where interfaces engineers have been getting to. Engineers that, let's say, were out of central casting, they're very good at what they do, but they're very good at only what they do. They started to see new ways to think, and then they got that bug that Mike talked about, and they would come to work with very different ideas. I knew we'd succeeded when one of the most classical ones called me up and said, hey, I got this little problem. You know, OSHA makes us put up these maps, colored maps by every doorway about where all the fire apparatus is and stuff like that. And the sun keeps fading the inks, and we have to keep reprinting them. My colleagues want to buy this chrome ink printer, and it looks like it's got really nasty stuff in the inks. Is there some way we could stop the maps from fading? Is there something we could put over it to block the ultraviolet? Out of the box thinking. I said, bingo, yeah, go to an art supply store. They have that stuff. And he was so pleased with himself for having come up with that original solution. It just illustrated the rearrangement of his metal furniture by redesigning stuff like pumps and pipes and buildings and motor systems. And it's contagious. I think he and others that started designing that way, it caught on in your culture. And
Okay.
Now it's spreading on its own. It's a
Thank you.
beneficial social virus.
I think I'm going to just pick up the pace a little because we're going to start running out of time. But we did want to talk a little bit about barriers and some solutions to scalability. So let's first, maybe any of the panelists, take on the education system, which traditionally has always been silos. And what's your recommendation or sense of where does that have to go to have a more interdisciplinary engineering or architectural or design approach?
I taught at the University of Colorado for many years, so I really know of how tough the School of Engineering is, at least at that university. And it basically is looking at professors that have been teaching the same thing year after year after year. They feel comfortable with that. And the curriculum, accreditation, stays the same year after year, where you look at the courses that really should be totally remodeled to today. Also, the way we teach engineers, you're given a test with a given on it. Okay, here are the known variables. Here's the problem, solve it. We have got to stop doing that. We go, here's the situation. What do you think the problem is? Completely turn around. Get the engineering students involved immediately into this out-of-the-box thinking. Don't hand feed them stuff and with formulas and everything. Get them to dig it up and get into real life things. And get the professors, like I mentioned earlier, trained, comfortable into this whole thing. We hire engineering interns all the time. The professors should go out and be interns in companies. So I'll leave it at that.
Actually, Nancy, maybe you could add to that and give an example of the lighting institute that you hold every year.
We have with just training, it's training lighting educators. And what happens is that they win these scholarships to come, and it's really highly competitive to go to the University of New Hampshire. And we accept about 60 lighting educators. They're there for 2 weeks, and they are there learning from top designers, from educators. And part of it is just not learning and getting up to date on new materials, teaching styles, but then they have to teach. So they practice and they go out in the field and do things, and we're all the students, the educators, and it's so successful. And they have looked at thousands and thousands of people that have graduated from this thing, all expenses paid, teachers can't afford to come. So this would be a great service that RMI could do to bring educators in and have a kind of a competition. So that's an example.
Great model. And do you find that they come out learning how to ask different questions, which, as you say, is the hard part?
Oh, not only asking different questions, But they now know the different things in the field. What are LED lights? What are compact fluorescents? Where could you use them? We actually bring them outside, and they have a little competition, line design of lighting, sculpture or building, and they have parameters. Has to be energy efficient, can't pollute the sky, has to be totally controllable, a thing of art. I mean, all of these parameters, and say, this is real life. This is what we have to deal with. And so they have to practice with it. But it's a wonderful model.
So it's not like deliver 50-foot candles on this surface, how do you lay out your troffers? Which shouldn't be there anyway, because as you taught me, thank you, you have to light surface, not volume.
So I'm going to just ask two more questions, and then we'll take questions from the audience. But first, so if it's that simple, why is it not more pervasive? Why isn't it ubiquitous?
I used to work for Edwin Land, who said people who seem to have had a new idea have often just stopped having an old idea. That's the hard part.
Mike, anything to add?
Give me that question again.
Well, I said if it's so simple and it's so obvious, why isn't it more pervasive and more ubiquitous?
Well, you know, it's an activation energy barrier, basically. It's the, you know,
There's that physical chemist coming out.
yeah, if you ever went to work in a factory, an old factory, like an old phenolics plant, and they're making phenolic resin in these big old pots in these real dirty place, and the lead supervisor, he's the guy that's in charge of making this phenolic resin and to make it perfect every time, okay? And he has a little black book, and he does make it perfect every time. The new guy comes in and he struggles. He makes a batch that doesn't gel, or he makes a batch that blows up, and he gets a little bit of advice for, you know, from the old master. But the old master never really brings out the little black book. He tells him just enough so he doesn't get killed in the plant, but not so much that this kid's going to take his job. Well, that's part of the heart of the problem. That reality exists everywhere, especially in industry. Okay, well, it exists everywhere.
I think it's the reality of implementation. You're
And it's a
exactly right.
barrier.
Mhm.
See, and that's when, as I was speaking about earlier, getting an environment, a corporate environment with a culture that gets built into its DNA of freedom to make a mistake and freedom to try something new, freedom to discuss ideas openly and exposing your ignorance as well as your brilliance is a barrier that we have to get over, or we're never going to get from here to there. We're going to keep doing the stuff we've always done and keep getting the stuff we've always got, like more CO2 in the air.
So in the cell phone industry, when you first started out, the handsets were very expensive, and clearly, generally speaking, prior to that, a service provider didn't really subsidize things. But it fundamentally changed penetration and the acceleration of penetration. Are there any new financial models here that could be applied to enhance and jumpstart this?
Yeah, actually, I believe in Aspen, City Council is about to vote on one. It's called PACE bonds. If you go to PACE, PACE now.org, you can read about the idea. It's only months old, and at RMI we've helped Jeff Tannenbaum and Cisco de Vries hatch it into a real way to finance, ultimately, perhaps trillions of dollars of building retrofits. And that would actually help heal the split incentive problem, because the landlord that needs to fix the building could be required to do so, but would be able to get cheap capital and positive cash flow from day one. It's a really slick piece of financial design, and that can change everything.
Terrific, thank you. Would anyone else like to add to that?
Where I live in Santa Rosa, California, the county has put in place a loan program where someone doing energy efficiency or renewables on the home, actually that's incorporated into the property tax on the home.
It's
So
the
they,
same kind of system.
Same kind of story.
Yeah.
Great, thank you. So we'll start with some questions from the audience. And please. Yes, those mics do work. You just have to.
organizations on the boards that I serve have been building. And every time it comes up at the board meeting, I say, will this be an energy efficient building? And I'm always assured it is. And I'm assured it is because the architect is a green architect. And I've talked directly to some of the architects, and I have yet to find any, and these are some well-known architects, that believe in integrated design, at least from the standpoint of what I've been hearing today. Are there suggestions that you could give me, as I serve on these boards, the next time a building is announced to the board that there's going to be a new building built, and very often when that gets to the board level, a lot of decisions have already been made. In a practical sense, how could I help implement integrated design in these organizations? Oh, a few ideas come to mind. One is to ask whether the architect, as part of the deal, is willing to pay the running costs for the first 20 years. Another way would be to take our handy-dandy little table of particular building metrics, as quantitative measures of how the building performs, compare them with the proposed design, and see if you're anywhere near the best practice category, which also, by the way, works better and costs less to build. You could show the board the DVD we put out on the business case for high-performance buildings. That is designed for CEOs, and I think it will change a lot of their perceptions of what to do. You could do performance-based fees. Again, pay the designers for what they save, not what they spend. That has a very salutary effect on design. And you could take some of your fellow directors on a learning journey to some beautiful, efficient buildings, and then point out that, by the way, although it cost a few percent more or less to build, depending on how well it was designed, you're getting 6 to 16% higher labor productivity in this office than the old one, and that's worth about 10 to 20 odd times as much as eliminating the entire energy bill. If we want to be a competitive company, we'd better do that.
I think I'd even highlight the Door Hosier building right on the Aspen Institute campus, which is definitely a very energy efficient building.
I learned something today from Michael in terms of what they did at Interface, is they set a goal for 0. And I would just keep it simple and say, rather than an energy efficient building, is ask for a net zero energy building or better. And what that's going to do for the team is they're going to have to think outside the box. Yeah. They're going to be challenged, and they're going to have to deliver something. The other thing about a net zero energy building requirement is that a building that's put in place today, under its next major renovation, it more than likely would have to adhere to a net zero energy requirement. And so an investment made today on the design team to deliver you a building that's net zero energy capable is going to save that corporation money in the future when it does a major renovation or it needs to offset that asset.
Oh, I couldn't agree more. You kind of stole my lines. But the other thing is to go to buildings that your team has designed, and not just what they say it is. Talk to people using the building and operating it, and you will find out so much, because we design teams rarely go back to our buildings and take occupancy surveys. You know, a year later, 2 years later, what's working, what's not. The buildings that I've done that with, Way Station, I think I'm on year 15, going back every year and talking with them. I learned so much about what I could have improved upon. So make sure that your design team really does that, and you go back and talk to owners of buildings that they've designed.
Other questions? Yes, please.
First question was, have you looked at the metrics from the Door Hosier Center? So it's a 2-year-old, 3-year-old building now. I'm just wondering, have you seen, have they met their goals with energy efficiency? That's the first question. The second one was, I'm just wondering if you could elaborate a bit more on the energy decoupling of the utility. It's fascinating because California was successful for what it
Well, we did the line design for the building, and I'd love some data on it and see how it's working. Jeff Burgess, isn't he here? I saw his name on, he was the architect for it. He's not here. I mean, if Jeff does show up, it'd be great, but we would love some data on it. Back to the decoupling, it is amazing the transformation of the utility companies and what they do when their stockholders can only make profit by showing energy conservation. It's a whole different thing. We are doing research projects with the utility companies. One is in changing out cities of their street lighting to energy efficient products, but addressing the environmental concerns with them. Putting an IP address on every single street light so we can dim them and get virtual metering and the maintenance instead of these crews driving around and going, oh, there's a day burner or that light's out or waiting for a police report in. They get a printout in the morning, say this light is out and I'll tell you exactly what's wrong with it. Two-way communication. The utility companies are saying this is fabulous. It's going to minimize maintenance, and just the maintenance alone is just a few years payback with that. But this is what decoupling does. They're looking a whole different way instead of selling you more energy.
On your first question, if you just give your name to Ginny, I'll get you all the metrics and offline and get them to you.
Judy and I have just put about a 200-point data system in our banana farm in Old Snowmass. So instead of running around with handheld data loggers measuring one thing at a time, we will have 200 continuous data streams of everything going on in the building displayed for visitors, and as soon as we've commissioned the software, posted on the web. So the whole thing's a science experiment. Otherwise, we don't know how to make it better because we don't know how it works. On decoupling, I'll just give you a simple numerical example. In 1992, the biggest investor-owned utility in the country was Pacific Gas and Electric. They invested $170-something million that year to help customers save energy cheaper than it could be produced, even in existing plants. That created close to $400 million of present valued savings. Those savings went 89% to the customers as lower bills and 11% to the shareholders as higher dividends, so they both had an incentive to do it. The initial investment was paid for by all customers over the years as you would for a power plant, only efficiency was cheaper, so you did it instead of the power plant. Now, our former chairman of RMI, John C. Fox, ran that program, and he reported that the 11% share of the savings that the utility got was its second biggest source of profit that year. It was over $40 million straight to the bottom line at no cost, no risk to the company. And he says if you produce that kind of financial performance, your CEO is going to call you up every week and say, is there anything you need? And all the smartest people will want to come work in the efficiency division to advance their careers. But the key step that comes before the shared saving is you use a balancing account. We can talk offline how this works, to decouple the utility's profits from how much energy it sells. So you no longer reward them for selling more, you no longer penalize them for selling less. They become indifferent to volume. And this is a really good time to do that because a lot of utilities are seeing demand go down. And the CEO really feels this if by chance compensation is tied to stock price. I just heard a colloquy in which the head of a very large utility was telling an audience of 300 CEOs that I'm not a decoupling guy, I just want to put megawatts in the ground and get paid for them. Peter Darby of PG&E said, well, actually, you may have noticed your stock just tanked. He knew the guy's compensation was tied to his stock price. But you may like to know that in the same period, my stock went down only 10% because the street correctly credits us for being decoupled so that the reduced sales do not hurt our top line or our bottom line. You could see the other guy's gears spinning pretty fast. He wants that too.
Go ahead.
My name's Jeff Grebe. I'm a professional engineer in the HVAC industry. Been doing it for about 30 years now. Designed over 1,000 buildings, most of them exactly the way has been described as the bad way. A few good ways. We did a LEED platinum building down in Carbondale. Got a comment more than a question. One of the things that I've noticed in the past is once we get a project to work on, the first thing that we always do is we do loads. And loads are an instantaneous look at the heating and cooling loads of the building. And they really tell you nothing about the energy consumption of the building, or very little. And one of the things I would like to see is a requirement in the building codes and the energy codes that instead of loads, we do an energy model for every building over 5,000 square feet.
Yeah.
And what that does is it now all of a sudden, instead of having this arbitrary number of 100 million BTUs of load, all of a sudden you got a dollars and cents of energy consumption that the owner can see and he can respond to. And I think every project I've ever been involved in that does energy models, which take maybe 3 times as much engineering time to do as loads, every project I've ever been involved in that engendered discussions about energy. Now all of a sudden we could change the energy model and say, what happens if we put more efficient windows? What happens if we do better pumping, better lights, better controls? And then all of a sudden you're rerunning that model and the building comes out much, much better.
And then I want the model to say, and here's how many tons of cooling equipment you need, and how many CFM of fans you need, and their capital cost. I don't want to just look at the energy cost. I want to see how, if you spend more on super windows and better lights and so on, you can make that mechanical equipment smaller or simpler, or even make it go away and make the whole building cheaper. And then if you do that, I don't want your fee to go away, because it's usually a fraction of the cost of the equipment you spec. I want to get you paid for producing that better solution for the client. That gets us back to performance-based fees.
There's a question in the middle.
Where's Alok?
Alok's up there.
Yeah. Which ones are we at liberty to name at this point?
Definitely Michigan and Benson. And we're also looking at Yale, and we have students involved from Harvard, as well as a few others.
Olin, I think. A very innovative one near Boston. Olin. But we have involved the deans of many distinguished universities around the world. I can talk to you offline about, who are very keen to do this and to drive the pedagogic change through their faculties. And in fact, Hans Snow introduced me to Jeffrey Orsock, the very dynamic new engineering dean at SMU. He's very keen to do this too. Yes, including Stanford. And it takes longer. We had some Stanford engineering profs who are just terrific, many of whom actually came to my lectures there a couple of years ago. And some of them really got it and want to change things, and others, I think, were quite comfortable with the way they'd always taught it. So it's going to take some leadership, bottom up and top down. One of the tricks we want to use is design the casebook so it is intelligible to freshmen, not just to the juniors and seniors who've learned a lot more and maybe lost some of their imagination along the way. We want to have the freshmen, as they work their way up through the system, be driving change by demanding different teaching than they had been getting. After all, it's their money and their time. No, everything. We want to cover every engineering discipline, and we are still weak in some on examples, but we're starting to get them trickling in. So, you know, electrical, mechanical, civil, chemical, electrical, electronic, software, aerospace, biomedical. We want to cover the whole thing.
Just to add to that, Dan, Stanford has something called the Precourt Center for Integrated Multidisciplinary. They're just studying the same problem, and Emory obviously is working very closely with them.
Hi, my name is Nick Eisenberg. I'm a freelance reporter. I need to be able to talk about this stuff to people who don't know they care. And one of the examples I want is how much bigger was the pipe? In your original example, you said that they made the pipes wider in this factory. How much wider?
I'm afraid I don't know the exact answer to that.
There were different pipes of different sizes, but I mean, sort of in the air, it might go from this big to this big. It's not a huge difference because of the fifth power relationship. No.
No, it's not like going from 2 inches to a foot, exactly.
Well, remember my example will go from ½ inch to 3/4 inch pipe, and over 6/7 of the friction goes away.
To put linings on the inside of pipes to reduce friction, even on long pipes. And
Yeah,
stuff.
you can do that too.
Yeah,
Maybe
you can use chemical means in order to, like Teflons and, things like that, anti-slip and things like that would accomplish some of the same concepts.
Yeah, and in the oil industry, they put long, slippery polymer molecules into oil to help it flow better.
Right. So the
Yeah, I mean,
concepts are
people
basically
don't
the same.
normally think about pipes and pumps. I just use that example because it's a real simple one. Maybe a house that keeps you comfortable without a furnace or an air conditioner but costs less would be a simpler example for most people.
At the top.
Does anybody on the panel or even in the audience know if Boeing knows about large pipes, small pumps in connection with the design of their Dreamliner? Would they? I'm sure it applies. Do they know about that?
They do now.
Is it in the plan, or is it too late, or?
I can't comment, but it's we are pursuing this line of reasoning in land, sea, and air vehicles, both civil and military.
The middle there and then top right.
Really? I want to learn about that. We don't have that opportunity here.
Yes, please.
John, I wanted to ask a question. I beta test some CAD software, and I ran across a piece of software called Console Multiphysics, which looks at multiple physics problems related to some object or some consumer product. In the architectural CAD world, BIM is becoming a big deal, and I'm curious about how Autodesk is approaching the integrative design aspects that we're hearing about here in terms of energy, lighting, the building shell, and heat loss and gain and that sort of thing, and modeling it within the software.
Thanks for the question. The Autodesk has really been on the forefront of, and the acronym the gentleman uses, BIM, which stands for Building Information Model. And it's a new generation of, new generation of CAD that essentially has intelligence embedded in the model, which enables you to very quickly and automatically do analyses. And so we have software today that essentially takes weeks, if not months, worth of analysis work and shrinks that down to minutes, if not hours, using this multi-physics analysis capabilities from energy use to thermodynamics to fluid flow to daylighting to all the weather conditions outside, how much rain is falling on the building, how much renewable energy potential there is on the building, what wind energy potential there is, the total water use in the building for all the systems, what are all the efficiency potentials for that water use, for lighting use, for energy systems. And so it greatly puts in the hands of everyday practitioner, you know, an expert like Amory, for them to really gain intuitive experience very rapidly. And one of the things that this does for the industry is an individual like Amory or other experts out there, they had to go through a painful learning process that typically took years of doing these individual analyses and having their aha moments of how to do something right. So this really shrinks that time down very rapidly to allow a lot of people to go through a lot of iterations very quickly and see the potential of where they very quickly learn what is the wrong direction and what is the right direction.
So this sounds like a wonderful tool, but if I were, let's say, the lead architect designing that retrofit of the Empire State Building, would it coach me in that integrative design direction, or would it simply tell me the consequences of my choices, but it's up to me to realize how to put together the window and lighting retrofits and save the money on the cooling and so on?
Today, it's really dependent on the user to determine what the right direction is. And either they have the past experience to where they know if I go in this direction, it's generally going to be the right direction. But with the tools, because the speed of analysis is so fast, is they can quickly, you know, essentially know they're going in the wrong direction sooner, so they can correct that. And so the aspect of what we're challenging our designers and engineers is to do a lot more analysis today. To solve today's problems, they have to do a lot more. And we're essentially making it easier for them to do that. So if Autodesk is successful with our intent here, essentially we'll make it easier to design a net zero energy building than it is to design a conventional building.
So are you saying that's built into Revit now?
Revit and Ecotect Analysis has that capability of doing all these simultaneous simulations for these different disciplines. And then we're really working hard to make interoperability with our other tools for daylighting analysis, you know, the fastest, most accurate tools, so the team can work much more collaboratively in that integrated design approach. So it really, you know, we're trying to meet the envelope of where things are going and trying to actually pull people into that new realm as quickly. Moore's Law, yes, as well as a lot of enormous amount of data. Some of these systems, you know, we have the world's largest weather database where we can provide hourly weather data to almost every location on the planet within 7 kilometers. And that's, you know, over 5 terabytes of data. And so that sort of information you just don't, you know, download on the internet, but we're putting it in the hands of practitioners everywhere so we can rapidly do this transition.
And what I would hope is that those become tools in design, but not the design means. Because as an engineer, like this wonderful mechanical engineer was talking about, you know, we are used to loads, everything, and we're trying to look at how do we blend the human factor into design? What is, maybe instead of a snapshot for daylighting, like on March 21st or June 21st or something, maybe it's more like autonomy on looking at comfort. What is comfort? What is satisfaction? How do we model that, you know, into this whole thing? Because we're so limited, you know, it'd be great to be able to bring in these other elements into our design.
Right, and that's sort of entering the world of cloud computing, where we can do not just the simultaneous analyses to get to that result quickly, but actually, you know, do that in really significant rapid to try all these different parameters to actually get to the solution faster.
What would be really neat is if the model can steer you through complexity to simplicity, steer you to the net zero building that is passive, cheaper to build, costs about nothing to run, gives a superior experience.
Right, and that's the direction where we're wanting to go, is simple is better.
Thank you. Any more questions from the audience? Yes, please, in the back. let me try and repeat the question. What would a new, fresh graduate today be different from about 35 years ago, and how would they differentiate themselves? Is that fair?
I would say that, the work that they did in college was, everything that we spoke about here, outside the box. When I was growing up, there was a bumper sticker. It was question authority. And I think any student who decides to do a project outside of the realm of the normal and to solve a problem that they see out there is really going to stand out as an independent thinker that's really looking for solutions outside of just following the tests and standard approaches. I think that from my own experience, that's what I found is doing that.
And one thing I've noticed is that the students that we get in our office, the interns, they are not one bit afraid of technology.
Yeah.
I mean, the modeling, everything. Oh, yeah. I mean, this is a no-brainer. Where a lot of us are going, AutoCAD, sure, that's why I hire people to do. But to them, it's the beauty in what they do and their analysis and modeling. It's awesome. And I think that the balance that they bring to the experience we have is a wonderful blend. And also, I think a blend of gender. I noticed that the women on my staff design very differently than the men on the staff. And I love the blending of the two. Different age groups, different gender, different cultures makes for an awesome project.
The yin and the yang. So let me suggest on that great note, we start heading over to the wine and cocktails, and we can continue the discussion outside. If you can just ask your question to the panelists right outside. One last thing, in this modern day, I got a question on the BlackBerry saying what are next steps and how can the audience get involved. 3 main areas. Amory and the team have really quantified the funding for the project is about $2.2 million in these first few phases. Certainly, RMI would love to get additional funding. The second is educational materials. They don't want to be overloaded with just basic case studies, but if anyone has terrific case studies of what innovative work is getting done there, please do send it. And lastly, it's partnering. This is a very large effort. It's an audacious mission. And whether it's corporate partners, whether it's academic institutions, engineering schools, trade associations, that would be very helpful. So I just wanted to thank you all for attending, thank the panelists for being here, and thanks RMI.
Thank you.